not great quality, but you'll get the audio. And then
Okay.
I'm just going to record my stream directly today. And we
Okay.
can post that.
Okay. What are you doing that is so cold? What were you doing yesterday? The fan?
Oh, we were playing with a fan.
So what are you playing with today?
What were we doing? We're going to do a little more with the solar kit. Then we're going to move over to the snap kits
Oh, the snap kits. Okay,
and kind
cool.
of do a mix of the two. Really take some measurements
Okay,
with it,
cool.
and then potentiometers and diodes,
Okay.
and I think that's it. Capacitors. I knew there was one more.
Okay.
Yep.
Well, I have to let you guys be. Unfortunately, I have to spend
Oh,
my time grading.
lucky you.
Oh yeah. I would rather be doing I would rather doing circuits, believe
Oh
me.
yeah.
Even though I'm not big on
I was gonna
circuits.
say, and I know how much you love circuits.
I know, right? But I have to grade.
Yeah.
So guys, enjoy. If you need anything, please make sure that you let me know. So I'll leave you hosting the thing. I'll keep it on just in case.
Yeah.
Um,
Yep.
so I'll be just here in the background. Okay.
Okay.
Okay. Talk to you soon, guys.
Let's see. How's everybody doing today? Go ask Google. What's wrong? Oh boy, I love it. All right, what did we leave off doing yesterday? We were looking at. Oh, we were playing with a fan. We were playing at the fan. Oh, yeah, I'm good. I get to play outside after I got off the call with you yesterday, so I was pretty happy to kind of walk around and kick the soccer ball around with my kids and ride bikes and things like that. So it was good. It was a nice summer day. So I hope you had a nice summer day too. What are we going to talk about? We're going to start with a little bit more on polarity. Um, you have two of the three fundamental laws of circuit analysis. I'm going to give you the third, um, and I'm going to give it to you a little bit of out of order because we need it to do what I really want to do, which is play with polarity and a diode. So we'll play with the diode a little bit, and we'll hook all of that up. I hope I have enough pictures to make all this work today. So we'll play with the diode. Once we do that, we'll flip over and we'll start playing with the snap kits, which I have on the floor next to me here. And we'll do a little bit of a mix and match between the kits, and I'll explain why we're going to do that when we get to that point. And then play with some capacitors, look at energy storage and potentiometers, how to vary voltage, a really common circuit that's important to just about everything we do. So we can build one of those with a potentiometer and play with that a little bit. So let's get started. Unless there's any questions or anything I can do to help you today, um, let me know in the chat. I have it up here, and we'll go from there. So hopefully the writing is the correct direction. I think I finally got that setting to be persistent. Okay. Am I backwards to you? I'm backwards to you, aren't I? Is the writing the right way around or backwards? Oh, okay. Cool. I've been recording videos with this. This is the first time I try to do it a lot live. I had a couple students try it out with me earlier, but they didn't say anything. Go figure. Okay, so polarity matters. And I think we kind of saw that with the fan, that if we change the polarity, right, the direction of the current and the direction of the energy drop, then it's going to change the direction of the fan, right? So I don't want to name the school. I'll just say it's a really large state school with a dog for a mascot. But I was helping some students there. I'm I sit on the board for IEEE Connecticut, which is the Institute of Electrical and Electronic Engineers, and so I'm the chair of student activities. So I get to talk to students at every university in Connecticut, which is kind of fun for me to get off campus once in a while. This has been too long off campus for me, but I was helping students at another state school, and these were graduate students. They were seniors. They were interning at NASA. They were, by all accounts, strong students, and they put together a competition to race boats in a lake. And one of the groups built their boat. Everything was working. They tested it out. They put it on the starting line, and they forgot to check the polarity of their motor, and their boat started going backwards instead of forwards. So everything can work out of the water, but you better make sure that the little propeller's going back, pushing the right way. That was pretty funny. I chuckled. I bit my tongue. I didn't say anything. I said, that was really good effort. So, I think my students would have pulled it off, no problem. Okay. So polarity with a fan matters, and their propeller was really just a fan pushing in the water. The next natural thing to talk about polarity is a diode, and that's a device that polarity is going to matter again. And because polarity matters in that case, it can control the flow of current. And if it can control the flow of current, we say that it's not passive. It's a semiconductor. It's kind of the first semiconductor that we introduce when we're studying this stuff. But if we don't want to blow up our diodes, then we better talk about resistance first. And we also have to kind of clean up the last fundamental, not so much boom, but maybe like fizzle and smell bad. So release the magic smoke, as we like to say. It could happen. It might not. It might be able to handle it, or there could be some internal resistance to your voltage supply that prevents it from happening. But we don't even want to risk it. Yeah. Yep. So let's see. Okay, so I'm trying to figure out how to mute Chase. Sorry, Chase. Audio. There he goes. Thank you. Oops. Okay. Cool. Okay, so we're going to look at our first little circuit, and we got to deal with Ohm's law. When we deal with a resistor, polarity doesn't matter. It's just going to make heat, and that's really all it does. But it makes heat, and it dissipates some energy, and that can be useful to us. So we want to make sure that we're dissipating enough energy in the resistor so that the diode doesn't go pop. That's our goal with this circuit. So that leads us to the last of the three fundamental laws of circuit analysis. Mechanical engineers, everything's going to be Newton. For circuit analysis, everything should come back to KVL, KCL, and Ohm's law. Okay, so this one's going to be Ohm's law. Okay, so let's see. This Ohm's law, George Ohm, don't search it. This is my favorite bit of nerdy electrical trivia that I usually ask students what country they think George Ohm was born in. And he was born in the late 1700s, I believe. And I usually love the answers I get because nobody gets it right. I usually get Germany or Austria or Prussia. Somebody even pulled out Prussia, which was pretty cool. But he was actually born in the Holy Roman Empire, which still existed. Ohmland, yeah. So that's, I can usually get people in class on that one, just to break it up a little bit. But he was relating the amount of energy dropped across something to the amount of current flowing through that same something. When we buy them from the store, we call them resistors. But everything has resistance. Even you have resistance, and that's maybe why you shouldn't, grab the two prongs coming out of the wall socket, because you're going to have current flow through you. But when we work with resistors, let me grab one here. If I can find it. In my pile of components, when we buy resistors from the resistor store, come on, focus, not on me. It looks something like that. Maybe the picture's better. It's this little thing down here. I'm not sure if that shows up for you. Ready? Let's do this. Bye, Falcon. That's a little better. It looks like that. So you have a couple of those in your solar kit, and I think they might all be the same value, but I'm playing with the one that has a green stripe, a blue stripe, and a black stripe, which tells me that it's a 56 ohm resistor. So there's a color code because it's too small to write letters on and numbers, so we do things with colors. Okay, so we're going to use Ohm's law, which just says that the current flowing through the resistor times the resistance is equal to the voltage. So V equals IR. So I'm betting some of you have heard that one before. Just a guess. We're going to take some basic measurements around that resistor and just see that they're right. So again, we're going to be practicing with the multimeter and hopefully getting some values. So the circuit I'm going to have you build, I drew down here as a schematic. Okay, and if you want to measure voltage, then you can take your ohm meter. Take your multimeter, set it to DCV. Okay, so I have that set to DCV, and I have it on the 20 because I think that's going to be about right. Let's get some fresh readings off your battery. Maybe some of you charged it last night off the solar panel. Maybe some of you didn't, or left your circuits running all night and it wore down. So in order to measure the voltage in this circuit, and you don't even need the resistor right now. Oops, I wanted red. I wanted you to stick your red probe here, and I'm using white for black because it shows up, and your black probe down here. Okay, so go ahead and measure your battery pack. So it's going to be red to red and black to black with your probes. Experiment number 7, champs, in the solar panel kit. So if you look at this manual, and I believe it's Lab 7, which is totally a cool one. And if you want to keep playing with it, you have these kits for a while, for starters. So you can play with Lab 7, charging the batteries with a solar module. Which is really as simple as putting them in series and hooking it up. Stick it out in the sun, let it bake. Okay, where'd my resistor go? Oh, good thing I have more. Okay, so measure that voltage, 3.7. Yeah, that's about right. Okay, now measuring current, we got to remember that current is a flow rate. So we have to count how much charge is going through. 3.75. These are still pretty well charged. Those are good. So to measure current, we got to break the flow. We got to get rid of a bit of wire and be able to count the charge flowing through that little bit of wire. So oops, that's blue, sure. Rewire that. So we break the circuit, okay? and we put the ammeter in there. So it's still the multimeter, but we turn it to be an ammeter. So we'll turn it to DCA. And is that behind my head? Yeah. We'll turn it to DCA, and 200 milliamps should be sufficient to do this. And we let the current flow through the ammeter, and as it flows through, can you see the image, Sham? Is my image not big and showing up for you? Not all of it. Oh, the image. Oh, the picture. Gotcha. Okay. Okay, so we're gonna let the current flow through the ammeter. That's okay. I'm glad you're. I love when you tell me what you need to understand what I'm talking about. It helps me out. So, thank you. Sincerely, thank you. Okay, so that's the schematic representation of everything, which is great. But I thought a physical representation would help as well. So the red probe is in the center hole, the black probe is in the ground hole down at the bottom, and then I use the alligator clips again just to make clipping things easier. So the alligator clips clip to the black probe and the black side of the battery. So that I'm thinking of as that bottom node. Okay. The red alligator clip I clipped to the resistor. Okay, so make sure you're using the Roy G. Biv, the green, blue, black resistor, which is 56 ohms, and just clip one side over here. And then you can take the measurement by touching the red probe to the other side of the resistor. And that should give you the reading in milliamps. So go ahead and give that a try. Let's see what we got here. 62, 60, 59. Yeah, that's about right. So we have to touch the red cord with the red alligator. So I'm going to touch this probe, this red probe. I would touch that right there. So come on, right for me. Come on, right. Make contact between those two things. .65. That's on the low side again, Shams. Man, I really wish I was there to see and help you troubleshoot that. Okay, so let's see. I got to pull somebody's numbers. Josiah's got 62, 65. So let's go with his numbers today. I'm trying to spread that around. I'm sorry if I haven't used your values, but let's see. So Josiah got 3.73 volts, and if we're following Ohm's law, and where did his current go? 62 to 65. I don't know. Let's pick something in the middle, right? 63 milliamps. Then that should be around 56 ohms. Now, we don't buy those, and they don't measure 56 ohms exactly. There's some error in the part value, and it's usually within 5%. 64, 66 with Juan. Okay, so I'm gonna go ahead and do the very little bit of algebra necessary to solve for this resistance, and we get 3.73 volts. over 63 milliamps. That's a horrible M. Okay, and if I go ahead, I'm going to pull out my TI-85 here and do 3.73, and when I enter 63 milliamps, I'm going to enter it as 63E negative 3. And then I don't have to think about the prefix. Okay, so from that, I calculate 59.2 ohms. So it's labeled 56, but our quick little calculation here tells us that it's closer to 59.2 ohms. So the other band of the resistor, it's green, black. Let me grab one here. Green, blue, black. And then the fourth band is gold. And the gold tells me that it's plus or minus 5% of the part value. So the part value is 56. We measured it as 59.2, but gold band is 5% tolerance. Okay, so 59.2 minus 56 over 56 gives us our error. So it's going to be 3.2 divided by 56. Okay. And if we multiply that by 100, we get it as a percentage, of course. So I'm going to write it as 5.7%. Oh gosh, we're even out of tolerance. How horrible is that? Okay. Okay, get your money back. That resistor is probably worth 1/4 penny if you buy it in bulk. So you got ripped off. Anyhow, so pretty close to 5%. Not too bad. And there could be other sources of error. There could be error in each of these measurements. There's no saying that this multimeter is calibrated. So those could be a little bit off as well. And then you have to ask how that's going to affect the measurement. So I wouldn't take that as truth necessarily without a better piece of equipment. Okay, so we measured the voltage, we measured the current, and then we calculated the resistance. The next thing I want you to do is just measure the resistance. Okay, so I don't have a picture for this one, but I think you can handle it. I want you to take the red and black clips and take the resistor just by itself, okay, and connect the red and black alligator clips to either side of the resistor. Nothing else can be in the circuit. Everything's got to be out. Otherwise, you're going to give current other paths that it can flow, and it may load down the voltage differently and change the measurement. So just with this red and black connected to either side of the resistor by itself, the dial should be on, you can put it with the little omega, make myself big. With a little omega, you can put it on 200. Okay, because we're expecting it to be around 56. So 200 is going to be a good top of the range for us to work with. Okay, so go ahead and take that measurement. I'm particularly interested in Josiah's, but everybody should give that a try, and that's how we can measure resistance. .6, 55, you know, and everybody has the same resistor that probably from the same kit, and we're getting some variation in all these numbers, right? So it's around 56, 55.7. That's, you know, that's really good. 55, 54. That feels like it's in the ballpark. Juan's got a nice one as well, 56.6. 56.3. Wow. Okay. So there's some error in one of these measurements. We took 3 measurements to make this happen, right? We measured voltage, we measured current, and we measured resistance. And they should follow Ohm's law, and they closely do, but not perfectly. So one of those 3 measurements has error, and it's not unheard of. Wire isn't without resistance. So even the probes that you're connecting to the circuit have a little bit of resistance. Measuring something always changes the value, right? So the way that your multimeter is constructed is going to change that value a little bit, and all of this contributes to the error. But I think we're within 5%. I'll take that 0.3. That's like we're a little closer in our percentage of error, and it's not bad considering the quality of this particular multimeter. Okay, so resistance is this relationship between how much energy we're dropping and how much current's flowing. There's a cartoon. It makes its way onto Reddit pretty regularly, and I'm trying to find a good one that kind of graphically shows these. It is a cartoon, and I think you can understand it better than this. But the relationship between voltage, current, and resistance is that voltage is the thing doing the pushing. The charge, the flow of charge in amperes, is the thing being moved, and then the resistance is if you want to measure the resistance, Shems, just connect the red and black leads to the resistor by itself. And then if you want to do your own numbers, if you have a calculator with you, V equals IR. So take the resistance, take the current, multiply them together, and you should get the voltage that you measured. But there's a couple other little things that come into play with that. So it's not going to be a perfect calculation. Okay, so resistance is resisting the flow. When I talk about this, I usually talk about cars going down a highway. I like that. I don't know. That's another thing that we can experience, right? Like we drive a car down a highway. It's something that we can relate to, rather than electric fields and little electrons moving in that electric field. Cars moving down a highway. So if a lot of people want to drive down a highway, and the highway only has one lane, you can only move so many cars down that highway. So it's going to restrict the flow of vehicles, right? So if you add 2 or 3 more lanes, that same number of cars can move down the highway using a lot less energy. So all of these things are in balance, and none of this works if you're driving through the city of Hartford. So that all of my analogies break down in Hartford. So what is the multimeter? 3.52. Okay. Because of the 200. So disconnect the circuit. Let's see. Let me see if I can get a picture to you quick. So the 2 measurements that you take with this, one of them's voltage and one of them's current. Okay, so measure your voltage by placing your red probe to the red lead of the battery, black probe to the black lead of the battery. Let's see here. Let me not lose my diode. That could come in handy. Okay, I guess I didn't have enough pictures today. Where's my battery pack? You might just get a brown background on my desk for this one, which is okay. So I'm connecting the black lead to the black probe, and the red lead of the battery to the red probe. Okay, and setting the meter to 20 DC V. Okay. And let me, my high production value here with my cell phone, so just give me 1 second. Luckily it automatically uploads. Okay, so let me do that. So measure your voltage this away. Come on. There we go. Oh. Okay. So I measured my voltage that way. And so black alligator clip. Oh, you can't see it down here. It's connected to this black lead down here. It got cut off the photo. And then red lead to the red probe with the red alligator clip. Okay, 3.64. So that's your voltage across the battery pack. Okay, the next one that we measured was this way, and I think you got that one, but it was very small. So build this one. So black lead to black probe to the black side of the battery pack. That one doesn't move. Disconnect the red alligator clip and clip it to one side of the resistor, and then with the other side of the resistor touch it against the probe and change the meter to be DCA 200M. Okay, and that'll be your current. And then the last thing you do to test it, oh, here's my resistor. The last thing you do to test it is disconnect everything else and clip the red and the black to either side of the resistor. And then you change the meter to be in the omega area, and 200 should be sufficient for that. So let me try to get another picture of all that for you. Okay, let's see, close that. And, whoops, oh, didn't upload yet. That was too quick. Okay, and I want to rotate that. Here we go. Okay, 62.5, okay. And then I measure mine as 55.4, and it's labeled 56. Okay, so let's do that calculation again. I'll do it with Shams numbers. And I'll do that. I can do that on the screen for you, actually. With a nice emulator. So let me see how I can, let me get it set up over here, and then I'll slide it over for you. If I can. It's far too big. Okay. So hopefully you got that measured up. Of course it's off the screen. Come on, let me make you smaller. Let me make you smaller. This is otherwise a very nice emulator of a TI-84. But I do wish I could fix the window size. I'm moving it. There we go. It wouldn't let me grab the side of the screen. How annoying is that? To make it smaller. So there's my TI-84. 56.3. Okay, cool. So the first number you measured was your voltage. The second number was your current. And the third was your resistance. And that's actually almost nominal value. It should be 56. You measured 56.3. So if Ohm's law holds, I should be able to take 62.5, and that was in milliamps. So I would usually enter that, since it's in milliamps, I would enter it as E-3, and then multiply it by 62.5, that's in ohms, and that should give you your voltage, and that came out as 3.9. It's a little high, but there's some error in all of these measurements. There's always error in measurements. So we have to hope that we're close, and close enough that we can see that the relationship holds. So this isn't great, but I don't think it's... oh, it would help if I use the right numbers. You were going to call me on that, right? 62.5 E negative 3. That was your current. 56.3. This is going to be better. 56.3 is your resistance. And so I calculate that your voltage should be in the neighborhood of 3.52. And you measured 3.64. So that's somewhat close. Okay, if we were being good, we would calculate the percent error and, try to get it within a particular range. Okay, so that's Ohm's law. That's the third fundamental law of circuit analysis. Ohm's did his work first, and he kind of played with all of this stuff, but he said, if I'm going to expend this much energy to move charge across an element, and it flows at a particular rate, then the material has a property, and that property is the resistance. So let's see here. Let me drag that back over. We can keep the calculator running just in case. What I love is that, well, I'll show you if the calculator comes back out later, but it powers itself off to save the battery, So it's like the real code from the real calculator. That's trying to preserve battery even though it's running in a window. So Ohm's law, Kirchhoff came in and did his work with his two other fundamental laws, his voltage law and his current law. Voltage law says if I put energy into a system and I return back to where I started, then all of the energy I put in has to drop back out, right? So all of the voltages around a loop in a circuit have to equal 0. All of the energy in has to come back out. It has to be conserved. For the current law, he said any current flowing in has to flow out somewhere. Otherwise, you don't have a complete picture of the circuit. So with those three things, we can build the rest of circuit analysis. And I really hope that I have all of you in class someday to teach you circuit analysis. But I can build it off of those three things. And for us, that's the equivalent of Newton's laws. Okay, so everything's going to come from that when you start looking at electrical engineering. Okay, but I started this out by saying polarity makes a difference sometimes. So up until when were semiconductors? We're talking probably the 30s, 1930s, somewhere in that neighborhood. Maybe even the 20s, depending on when it was in the lab versus when it became a commercial product. Semiconductors kind of make the world go round. And the first semiconductor that we introduce is usually a diode because it's the simplest of the semiconductors. And polarity matters for this type of device. If you have a device that you plug in a battery and you want some protection for plugging it in backwards, it probably has a diode in it somewhere to protect the circuit. It's not going to allow current to flow backwards. So if you do any plumbing, which I unfortunately have to some days, it's the check valve of the electrical world. So it allows flow in one direction, but if you try to have it flow in the opposite direction, it's going to slam shut and no current's going to flow. Okay, we have some fun ones that we can play with. Fun ones. Whenever I say something's fun, I'm always like, it might just be my kind of fun, maybe not your kind of fun, but you're all here with me, so I'm assuming that we have something in common. So we have some light emitting diodes. So there's plenty that are just used for circuit protection, and those are nowadays they're mostly made out of silicon. Some of them are made out of germanium. That was more common in the past. There are some applications where you still want to use a germanium diode. But a lot of diodes that we see, I can probably point to 5 of them if I just look around my desk right now, are, well, you know what? And now we've gotten fancier. And there's some of my room lights as well, are light emitting diodes. They're really efficient. They don't give off as much heat. So all of the energy that we're giving to them is maybe not, I shouldn't say all of the energy, more of the energy that we're providing to the LED turns into light energy, which is what we want it to do. We don't necessarily want it to be a heating bulb. So we're going to play with some LEDs, and polarity matters. Okay, we got to get the polarity right. So you have a part in your kit that looks like this, and I even gave you a warning down here. I have a feeling Casper's already hooked it up, and I hope it still works. But we want to be careful with it. You're not going to hurt yourself. I wouldn't let that happen. But you could destroy the part. I think there's 2 or 3 of them in your kit. If that does happen, as we speak, of course. So this is the schematic symbol for a light emitting diode. The only difference between the schematic symbol for a light emitting diode and just a regular diode is the regular diode doesn't have light shooting off of it with these arrows. So the whole point of this diode is to prevent current flow. So it's only going to allow current flow from left to right, as I have it drawn here, and it kind of follows this this triangle like it was an arrowhead. The side on the left here we call the anode, and the side on the right we call the cathode. Okay, and if the current's flowing in this direction, then we should get a voltage across it that looks like that. So we're going to have more energy on the anode than we have on the cathode. Okay, now physically what that corresponds to is the 2 legs of the LED. Okay, and the longer lead is going to be the anode. So over here I have it on the left, over here it ended up on the right. I should have flipped the picture. But it's the longer of the 2 leads. Okay, the cathode is the shorter of the 2 leads. I forget this all the time. I walk around not knowing which one is which one's the anode and which one's the cathode. And if I'm prototyping a circuit, I always have to plug it in one way and then turn around and plug it in the other. But we have to be careful. We have to restrict the flow of current. And if only we had a device that could restrict the flow of current, right? Well, that's kind of why I had to talk about resistance up here. All right, so we're going to build the circuit, and we're going to make this LED turn on. You might get away with it because there is internal resistance to the battery, and there's internal resistance to the solar panel if you want to go hook it up to the solar panel. So those 2 devices can't provide infinite current, but it might be enough current to make it go pop. So we're going to add a resistor to it. Okay, and we're going to add a resistor to the circuit in series. So here it is as a schematic. I think I have it all on the screen. Yep. Here it is as a schematic, and I put that one on the right because I'm down here and I knew that it could be up there without a problem. And here it is built out of components. Okay. Hey, Juan got it to turn on. So black lead from the battery pack to the black alligator clip over to the cathode of the LED, and then red lead of the battery pack over to the red alligator clip, and I clipped that onto one side of the resistor. Okay, and then since I'm on a white background I need black, and then touch the resistor, the other side of the resistor, to the anode of the LED, and it should turn on. It looks like Juan got it. Sham's got it. Nice. Woo! I love it. Okay, so it's on. It's dissipating energy, and some of that energy is being turned into light. Actually, most of it's being turned into light. A little bit of it's still being turned into heat, which it happens. It's not 100% efficient. That'd be awesome if it was. But that's our LED. And then we protected it by putting that resistor in place. Okay. Let's take some measurements and figure out what's going on here. So take another alligator clip. Flicker, flicker. Uh-oh. Are you making good contact between the probe, or between the resistor and the anode? Okay. Twist them together. Make sure all your connections are good. If it's flickering, that's usually not a good sign. But I'm going to take... I'll do this one live for you. I'm going to take my... And I'm going to make myself big, shiny, and bright. Cool. Okay. Ah! If I don't drop it. Okay, so I'm going to take my resistor. How can I get focus to behave for me? And my LED. And the longer lead is this one here. And I'm going to cross those two legs. And then I'm going to twist them together so that they stick together. Okay, so that it looks like... Is it better if I'm out of the shot? So that it looks like that. Okay. And keep the other alligator clips where they were. Okay, so the black lead clipped to the other leg of the LED, and the red lead clipped to the other leg of the resistor. Yeah, alligator clips work too. That's fine. Okay. So your light should be on now, right? It's just constantly on. And then I want to measure some voltages. So pull out your multimeter, DCV. I'm going to put it on 20, which should be good. So let's measure 3 voltages. Oops. Let's measure 3 voltages. Let's measure the voltage across the battery. Okay, so I should probably name these things. So we want to measure the... Come on, right for me. Come on, right for me. Okay, we want to measure the voltage across the battery. I'm going to do VS for V source. I'm going to do the voltage across the resistor, VR, and the voltage across the diode, plus minus VD. Okay, so this is how I would label it on a schematic. Oh, you don't see that. Sorry. Let me get that back for you. Whoop. Okay, so VS, VR, and VD. And that's how we would see it annotated on a schematic. If you want to go measure those, set the meter to DCV, and the 20 should be a good setting for all 3 of them. And for VS, put the red probe on the plus side and the black probe on the minus side. Okay, so the red probe is going to go, maybe I would touch it over here to the alligator clip, and the black probe would go over here to the black alligator clip. Okay. For the resistor, I would put the red probe on the red alligator clip and the black probe on the twisted pair between the two. Okay. And then for the diode, I would put the red probe on the twisted pair and the black probe on the black alligator clip. Okay, so let's make those 3 measurements. I don't have them, but you will. And let's see what they are. Okay, Casper's got numbers for us. Let's let some other people get in here too. .68 inches. Oh, that's for VR. Okay. Doop, doop, doop. Doop, 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 doop. Let me know if I need to repeat anything. Oops. .89 for 1. I'm guessing that's the voltage across the diode. Okay, Josiah's got some good numbers. 2.9. Yeah, it looks like you're all kind of in the same ballpark. I put the red cord to the resistance wire, the black cord to that. I got 3.63. Okay, that's probably, so that's VS for you, Shams. .86. I'm guessing that's across the diode. Let's go ahead and use her numbers. 2.86 volts. It's a horrible 8. Okay, it looks like VS is, what did she get? 3.63 volts. And then VR, so one on one side of the resistor and one on the other. What do you get for that one? .74. Cool. Awesome. 0.74 volts. Okay. So here's how this works. And I usually have to teach undergrads this. You're going to come in knowing it. You gotta figure out how big the resistor should be. And the diode is going to have a voltage that it prefers to settle at. It's called the forward bias voltage, and everything else comes out of that. With these three numbers in this circuit, we have a loop, just like we did when we were looking at KVL yesterday. If I go from here to here, I'm going up. From here to here, I'm going down. And from here to here, I'm going down. So if we go up across VS, 3.63, and now I go down across VR, minus 0.74, and I go down across, is this behind me now? Oh, I can't go any further. Hold on, I think it's best if I disappear. Okay, and I go down across the diode, 2.86. That should be 0. Now there can be some measurement error. Okay, but let's grab our calculator. See, the power went off. Save the battery. And we have 3.63 minus 0.74 minus 2.86. Okay, hopefully that's close to 0. 0.03, so we have a little bit of error, but not horrible. Okay, and that's KVL, one of our fundamental laws, right? Okay, so if we're going to size the resistor, how big a resistor do I put in there? If I make it too big, there's not going to be enough current to turn on the diode. If I make it too small, there might be too much current, and diode go pop. we want to avoid that too. So let's see here. Notes Thursday, and this should just be a blank one. Yep. Okay, so our circuit looks like this. I'll draw it again. Same circuit. But I'll walk you through how I do this. And it's such a common circuit that I think it's worth knowing. Okay, so let me make up some numbers. And I'll use more typical numbers that, here I can come back in now, that you may see in a microcontroller circuit or a computer circuit or anything like that. You may have a 5-volt supply if you're using old TTL logic. You got a resistor, and then, oh, I wish I could take a poll. I think I can. Well, let's do it informally. What color LED do you want to use? And I'll show you why that's important in a second. So like red, green, yellow, white. There's blue. You want to go red? Okay, 1 vote for red, blue. Okay. 2 for blue. I know, right? Blue looks so much cooler. I got a blue one on my microphone here. Blue was not a common color up until recently. And by recently, I mean like the last 15 years. But making blue LEDs was it wasn't that it was impossible, but making them at scale was impossible. So like blue LEDs, pretty cool things. Okay, so 2 votes for blue. I think you lost, Casper. I'm sorry. So let's make this a red, or no, a blue. Jeez. Let's make this a blue LED. Okay, so if I was designing this circuit, next time, man, next time. Okay, if I was building this circuit and I wanted to figure out what's going on, I would say, okay, I need a blue LED, and I need to know its forward bias voltage. So I would go to my friendly parts supplier. Hold on 1 second here. Whoop. That's not, whoop. There we go. Does that show up the right direction for you? Or am I is it backwards? Backwards? Okay, hold on 1 second. Easy enough to fix. Hey! How's that? Cool. Okay, thank you. This is going to be fun when I go back to recording videos and I have to figure out what to flip back from talking to all of you. But it's helping me for the fall, so thanks, everybody. Okay. I'm not endorsing this company at all. I will say that when I build things, when I'm consulting or when I build things for classwork or research, this is kind of the company I go to. They're expensive, but they have data sheets on everything. Okay. You might be able to find it cheaper on Alibaba, or somebody even reselling it on Amazon might be cheaper. But when we're building things and we're building things for a customer, we have to be able to stand behind our calculations. And if the company that manufactured these parts has something listed in a data sheet, then that's something we can point to and say, this is why I thought this number was good. So hopefully when the helicopter crashes and we get sued, we can have a paper trail. That's the not so fun part of engineering. Okay, so I'm going to go shopping for an LED, and I can come down here and I can say discrete LEDs, so it's just going to be an individual LED, and then I can shop by color. Okay, so amber, blue, some of them are multicolored, but we just want one that's blue. So I can pick off blue, and I can just say apply filters down here in the corner. And now we're down to, how many do we have left? Let's say in stock. So we're down to 974 blue LEDs that we can pick from. Hey, that's a good amount. So some of them look like this. They're little surface mount LEDs if we want to put them directly on a circuit board. But since we're experimenting and playing, I might want to use a through hole. So I'm going to pick through hole right here. And I'm down to 135. And now those look similar to what you have in your hands. I'm picking at random, so Cree. Let's go with Cree. You can buy Cree LED light bulbs at the store if you want. So they do a lot of LEDs, including LED light bulbs. So down here in the product attributes, this is a common enough specification that it's right here on the front sheet. So the forward voltage is 3.2 volts. Is it going to be exactly 3.2? No, but it's going to be pretty close, and we can use that as a nominal value to design around. Okay, so that's listed nicely because DigiKey is a pretty nice supplier, but it should also be somewhere in the data sheet. And so every component on here has a data sheet it's a PDF, and it's just got a mess of numbers. And I'm looking for the forward voltage. Let me make this as big as I can for you. Okay, so to read these quickly and find the forward voltage, I'm looking at the units. Okay, every number deserves a unit. And I know that a voltage is going to be measured in volts, so I don't even have to look at those two. This one is going to be the reverse voltage. That's how much voltage I can put across it backwards without making it go pop. So that's not quite what I want. But if I come down here, typical electrical optical characteristics, and I look at the units again, that's in volts, and there's my forward voltage. So that's how I read that data sheet really quickly. And it says the condition for this forward voltage is 20 milliamps. Okay, so 3.2 volts is the typical value when I have 20 milliamps flowing through it. Reverse current. The other thing we might want to consider is how much current I can push through this. I want to make sure I don't push too much current through, so I better look for a maximum amperage. So here's milliamps, and this is in the maximum table, and that's the maximum forward current. Okay, so that's 30 milliamps, okay, and 3.2 volts. So those are the two values I grabbed from there. So let me crop down a little further again and look here. So we get 3.2 volts is our nominal value here. Okay, and we know that we're going to have current flowing in this direction, so left to right, and we know that that current has to be below 30 milliamps. So let's figure out the range that we can set that resistance to without violating that 30 milliamps. Okay, in order to do that, we know the current going through the resistor. We need to know the voltage across the resistor. Okay, and we find that voltage by using Kirchhoff's voltage law. I'm going to start here, and the long bar is positive and the small bar is negative, so I'm going to go up 5 volts. I'm going to go down whatever the voltage across the resistor is, and then I'm going to go down 3.2 volts across the diode. And I'm back to where I started, so that should be equal to 0. So we solve that for VR, right? So we got 5 volts minus 3.2 is equal to VR. And if you do that little bit of arithmetic, you find out we get 1.8 volts across the resistor. Okay, so you measured that, right? And it was like 0.7 for the other circuit, or it's 0.74 or something like that. But if I want to pick that resistor, then the rest of it is Ohm's law. I know the voltage across it, nominally, and I know the current through it. So we think about Ohm's law, and we say 1.8 volts is equal to 30 milliamps times R. Okay, solving for R, we get 1.8 divided by 30 milliamps. Okay, that was in volts. Volts over amps gives us ohms. Let's grab our calculator again. 1.8 divided by 30 e negative 3. And that tells me I need a 60 ohm resistor. Okay, whoops, the calculator disappeared. Okay, and that's how I pick that resistance. Now, if I want to have some safety margin, do I make that resistance bigger or smaller? If I want to make sure I stay away from the 30 milliamps, do I add more resistance or do I reduce the resistance? Yeah. Yep, right. Squeeze that pipe down a little more, restrict the flow of current, and we're going to be better off. So I might not look for a 60 ohm resistor. I might look for like a 100 ohm resistor, because that's my limit, is that 60 ohms. So very good. Very, very good. Okay. Let's see where we go from here. What did I promise you next? Gotta look at my schedule. We're feeling okay about diodes in general. Yeah. Okay. Cool. Cool. All right. Let's talk about. I got two things I want to do. I think I want to talk about. Oh, yeah, where's the chart thing? There we go. 3? Cool. 3s are good. First time listening to me yap about them, I'll take a 3. All right. So I want to do 2 more things today. All 3s. I like that. That's cool. Pat myself on the back later. Some days I hit it, some days I don't. I want to do 2 more things today, and let me see if I can find the pictures that I took earlier, because a picture's worth 1,000 words. So let's see. Today is the 16th. We did that. Oops. We did that one. Okay, I want to play with the snap circuits a little. And, oh yeah, I intended us to do this with a snap circuit, so that we start to build with it. Let's get that up. Let me make sure I'm still looking at. Oh, now you're looking at the whole screen. I've ruined the magic of my drawing program. And let's do this again with the. Yeah, go ahead and take out the snap circuits. Keep the solar kit nearby, because I certainly want to use the multimeter, and I want to build this with snap circuits. I know Zoe's like a pro at snap circuits, but if you haven't handled them and played with them, then let's build this same circuit. Let's build it out of the snap circuits. Let's see. So we're going to build that circuit to begin with. And I have a picture. I built this earlier today. Somewhere. I just had a picture, I promise. Okay, and this LED is way cooler in the snap circuit kit. And it looks something like that. So snap circuits are neat. I think it's an easy way to prototype without having to like have a tangle of alligator clips on your desk. If you go take physics courses, physicists love to build prototypes with alligator clips, which is fine as long as the circuit's really simple. But if you're building anything more complex, we usually use something called a breadboard, which is a historical name. It's not actually a board that we make bread on anymore, but it might look something like. Nice. Of course you do. It might look something like. I have a poster. I have a poster somewhere, and it's almost complete, is the best part. I have to build one more thing for it. Posters. Where's my breadboard poster? This is how I get around copyright laws. I use my own posters. Okay, it's going to look something like this over here. And we can make the connections with that. So we can build some pretty complex circuits. I had some students last semester in the middle of all of this shutdown on breadboards. They built a whole processor out of transistors, which was a really cool senior project. They needed something like 10 breadboards to make a very, very simplistic processor. But it's really hard to argue with them that they don't know how a computer works when they can build one on a breadboard. So this is kind of a more typical thing to build prototypes with. I have a actual physical picture of one over here behind me. And then we can make nodes with it. And that's really all you're doing. With the alligator clips, when you clip two things together, you're making a node. With the breadboard, when you stick the leads in a group of 5, so you can see these, I have the orange underneath those are all connected. Okay. Then you're making a node. Okay. And then you have some nodes along the sides. So this is a little bit more, it's not even a professional tool anymore, but we do use them when we're prototyping circuits. The snap circuits are kind of just another version of this breadboard. We're just going to be making nodes with the snap circuits. Okay? And just by snapping them together. So I have a different circuit built on here, if you noticed, if you're paying real close attention. We'll get to this one. But for now, I thought it might be good just to build a familiar circuit and just make sure it's working. So we've got a battery. Let's see if I can get this all on the screen. Almost. We've got the battery over here. We've got the resistor, and we've got this LED, which is nice, Josiah. Cool. We've got this LED here, which I plugged it in, and I was like, it just says color. Like, what color is it? And if Josiah's got it working, then I'm pretty sure that Professor Amaya gave you batteries. I really hope she did. She said she did, and I trust her. You may be able to, if you don't have the batteries. Yeah, so maybe dig through the bag a little, because I figured that out last week when I was first playing with all this stuff, that there were no batteries with it, and I could see that going poorly. So, and she did the heavy lifting on organizing all this. So, oh, did you find them? Cool, sweet. Okay, you might be able to pull out your nickel metal hydrides if you had to. If you lost them or couldn't find them, the rechargeables may work. Okay, so yeah, get that going, and check out the cool disco light LED that they gave you. Which kind of drove me crazy, because then I couldn't do basic calculations around it. So while you're getting that stuff, yep. While you're getting that stuff, let's take a look at why it drove me crazy. Here's our blue LED, right? And the typical value was 3.2 volts. What did Casper want? He wanted red. He wanted red. Okay, so if we come back here and we look at a red LED. Did I get rid of the color? I got rid of something. Okay, and we look at a red LED. Sorry for scrolling too much. I know that makes it a little blurry for a moment. Okay, let's go look at a red LED. Like, oh, it's also Cree, so that should have the same style data sheet. And we pull up the data sheet for a red LED. What we're going to find is that the forward voltage, instead of 3.2, is 2.6. No, we're not doing a particular page in the snapbook. Oh, I'm sorry, I took the image down. I'll put it back up for you, Shams. Oh, that was private too. So the forward voltage on an LED is really going to be dependent on the color, and that comes down to the different. There's the circuit we're building right now, Shams. Sorry about that. I'll be good. I'll leave that up for you. I'll even crop it so it's a little bigger. So when this one started blinking at me, I went, well, that's not going to be a consistent voltage across it. And there must be something going on. Can I move the picture over to the left? Is this the left? Okay. No problem. Happy to help out. Okay. Disco. Oh, yeah. Okay. So whenever I'm building these snap circuits, it's always like, can I get the height right? You know, do I have enough snaps to make it everything level? But it's the same kind of circuit, and it's just a nice, easy way to prototype a circuit like this. So go ahead, for the rest of you following along, give that a try. Whoops, I don't want that. I think I'm good with that. We got some like real sourcing parts going on there. I want to look at my pictures. I think I meant for you to take the measurements with this circuit. Que sera. Okay, so it sounds like a bunch of you got it working. So I find not you, because you're just starting out with this stuff, but I find that even some of my seniors have a hard time moving from nice Zoe, cool, moving from the schematic to the circuit. Nice, Shams, awesome, I love it. You know, the schematic is an abstract representation of it. In mechanical, you're going to draw a free body diagram of all of the forces and moments, and for electrical, we're going to draw a schematic. But it's a picture that helps us analyze things, and it's not necessarily a physical representation. So, cool. So all of you all just built this circuit on your snap kits by following this picture, which is awesome. Okay. Take out your multimeter, and let's do some of those same calculations again, or take the same measurements. Okay, so let me draw on this. Okay, and get this color. So do a measurement with a red probe here and the black probe down here, and now you can just touch the snaps. Okay, and that's going to be, you know, I have a stylus. I should just draw with the stylus instead of trying to do it with a mouse. That's going to be VS. Okay, if you put the red probe here and the white probe here, that's going to be VR. Okay. And the red probe here. And the black probe here. That's going to be VD. Okay. Yeah, 20 volts DCV. Yep. And we should see the same kind of relationship. This thing blinking, I have no idea what that's going to be. I really have a hard time predicting that. That'll be kind of fun to see what you come back with that. I haven't taken these measurements yet, so I don't know. So while you're doing that, I think I'm going to build another circuit. See, what do you got? 20 volt. Okay. 2.46 VS. Yeah. Batteries are a little low, but that's okay. 0.1, 0.3, 0.03 for VR. And between 2.5, 2.2 to 2.5. Uh-oh. Make sure your probes are pushing all the way, Shams, and maybe wiggle your knob on the multimeter. Those are my first guesses. All right. The light's working. We'll take that, right? That's good. Okay. I'm taking one more photo. As we build another circuit here. Okay, so let me grab somebody's numbers. Casper's are right here at the bottom, so I'm just going to grab those. And I'm going to play the same game where I go up across VS. So that's going to be 3.22. Okay, we're going to drop across the resistor, which is 1.2. And then we're going to drop across... I'm trying to make sense of your numbers here. Hold on. 1.2 to 6. 2.7 to 1.8. Okay, it's bouncing around because of the color change. Yeah. Those are capacitors, and we're going to play with those in a little bit, Josiah. They're storage. By the end of today, we're going to play with those. They store energy for us, which are really cool. The F is the unit of capacitance, and named after Faraday. So capital F for respect, right? Okay, so minus 1.2, but they're bouncing around, so I got to pick my numbers correctly here. So let me see. Let me grab your 0.6, because I think that corresponds to the value when you have 2.7, and that should be approximately equal to 0. Okay, so if I pull up the calculator again and I go through that, I go 3.22 minus 0.6 minus 2.7, and we should end up, yeah, pretty close, negative 0.08. So again, there's a little bit of error, but we're in good shape. Okay, so if we can do it with alligators and clips and stuff like that, we can do the same kind of thing with the snap circuit kit. All right, so this is a pretty common circuit. Anything that has an LED in it has a resistor in series with it to limit the current. KVL holds. All of the voltages around the loop have to add up to 0, and we use Ohm's law when we want to size it. Okay, so everything that we do can come back to KVL, KCL, and Ohm's law. All right, so let's see. I want to talk about. We're going to do 2 more things. We're going to talk about a really common circuit. It's so common. It shows up in just about everything that we touch. And I want to look at that using discrete components. So we're going to use a couple resistors to build it. And then we're going to take a potentiometer, and we're going to use the potentiometer to play with it a little bit more. Once we do that, then we'll start talking about some energy storage. And I think that sets us up really nicely to move into tomorrow and hopefully play with some transistors and things like that sort. And the circuit that I'm introducing today that is so important shows up in transistor circuits. So we kind of have to have some comfort talking about a voltage divider. Okay, and we're going to build a voltage divider in 2 different ways. And the first way that we're going to build it is by using 2 separate resistors. Okay, so whoops, I'll draw it as a battery. I almost drew it as a generic voltage source, but we're using batteries. So I'll go ahead and draw it as battery. Ditch that so I can see what I'm drawing. Okay, and we're going to connect 2 resistors just like this. Okay, and it looks like most of you had battery readings for VS. We had one down at 2.46 from Josiah, 3.22. I think we can call it 3, and we'll be safe. Okay, and the 2 resistors that we're going to use. Hold on, I gotta look at what their values are. They're the only 2 resistors that we have in the snap circuit kit. So one of them is a 5.1 kilo ohm resistor. And the other one is super tiny. I hope this works out. Let's see what happens. They're the only 2 in the kit, so I'm using what we got. I can always wing it if it doesn't work out to a nice value. And we can start alligator clipping parts in and fun things like that. Let me do this calculation quick to see if this is going to work out. Divided by... Ooh, that's going to be tiny. That's going to be tiny. Okay, so let's talk about the theory. Let's see why this is going to be such a small number, and then I'll show you. I'll rebuild the circuit with some of the solar kit parts, and we'll make it work. Okay, so in this circuit, we know that this 3 volts has to drop as it drops across these 2 resistors. Okay, so let's call this VR1, and let's call this VR2. This circuit shows up everywhere thanks to another theorem called Thevenin's theorem, another French guy, dead French guy, where he said we can reduce any linear circuit into a voltage supply and a series resistor. So a lot of times we use Thevenin's theorem to reduce circuits to a manageable point. We say, okay, all of this stuff isn't changing. Let's just think of it as a voltage supply and a resistance. And because of that, we can hook up another resistor to it. Okay, and if we're thinking of some big circuit as a Thevenin equivalent circuit, this voltage supply and resistance, and we hook up another resistor to it, we end up with a voltage divider, and it looks a lot like this circuit, and that's why it just shows up everywhere. So it's kind of an important circuit in that respect. Okay, so how are the two resistors connected to each other? See what I'm doing? I'm quizzing you on yesterday. Sorry. No grade. So how are those two resistors connected to each other? Do they share a node exclusively? Do they share the same two nodes? Neither or both, right? Yep, they're in series. If we look at the nodes, let me gotta thicken up my pen a little so I can use it as a highlighter. Right, looking at the nodes. Right, I've got a node there. I've got a node here. And I've got a node down here. Okay, so the two resistors share the blue node exclusively. So they're in series. R1 and the battery share the orange node exclusively, so those are in series. So that we can say that these two are also in series, and they happen to share the red node exclusively. So everything's in series. There's only one current flowing through this. Okay, so there's only one current. Oh, I still have a thick pen up here. And we can call that I. Make that a little smaller. There we go. Okay. When resistors are in series, we just add the resistances. Okay, so this is, if I'm using my car analogy, the energy it takes to move along one section of road and the energy it takes to move along the subsequent section of road just get added together, right? So we're just making the road longer. It's going to take more energy to move a car down a longer road, right? Because we have to run it longer. So we just add the resistances together. So I can redraw this circuit this way. Okay. And since they're in series, we can say it's R1 plus R2. Okay, this is still 3 volts, and 5.1K plus 100. Okay, maybe I'm willing to bet most of you can do that in your head, but I really do like using the exponents when I'm using the calculator, so I don't screw it up. And here's a case where I have them mixed. 5.1K, I enter that way, plus 100, should be 5.2K. And it comes out as 5200. Not my favorite way for the calculator to be set. So I'm going to set it to engineering mode. And get that same answer. And I get 5.2, and now it's E3, so I read that as K. So 5.2 kiloohms. Okay, so this is 5.2 kiloohms. Okay, and it carries the same current. Okay, because they're in series, they carry the same current, right? So I is the same there. And I can calculate I. I can calculate I using Ohm's law because this battery is in parallel with this resistor, so I can tell you that there's 3 volts across it. So rearranging Ohm's law, we get something that looks like that. So let's get a real number for that. Okay, 3 divided by 5.2 K. Okay, and again, this is why I like putting in that SI prefix, because it comes out here as E negative 6. Okay, so when I write that, it's going to be 500. Oh, it drops off the. I lost focus. There it is. 576.9 E negative 6. So it's going to be 576.9 and that's microamps. That's millionths of an amp. Okay, really stinking tiny. But it's tiny. It's really tiny. So that current there is the same as the current over here. So if I want to figure out one of the voltages of these individual resistors, right, let's take this and head back over to the left, my left, although I'm starting to think that I'm somehow reversed, but everything is visible. I don't know what to make of that. So moving over to my left, maybe you're right, we can calculate V sub R1 by taking that current and multiplying it by the resistance of R1. So I'm going to plug in 576.9 microamps, and I'm going to multiply it by 5.1 K ohms. Okay, that's going to tell me what the voltage across that resistor should be. All right, so calculator. So we've got, that's our current. You know what? I'm going to store that in a variable for safekeeping. So I'm going to say whatever that current is times 5.1 K. And we get 2.94. That's not a big change. It's almost 3, right? Not quite, but it's almost 3. 2.94, and I'll do a little bit of rounding. Okay, so we can come back over here and say that VR1 is equal to 2.94 volts. All right. And we do the same thing for VR2. It's carrying the same current. It's in series. Okay, so we take the same current and we multiply it by R2, and that's going to be 576.9 microamps times 100. Okay, arguably I should be able to do that in my head, but I can only rub my stomach and pat my head so much. Okay, so we take that same current and we multiply by 100, and we get 57 point, let's call that 57.7 millivolts. Okay. So I was going to have you build this. Those are the only two. Let me see. I'm going to take a measurement. I was going to have you build this on the snap circuits. And we may still. Yeah, mine's connected. Let me see how close this gets. 57.7 millivolts is a really tiny voltage, and I'm not sure that this meter is going to read that accurately, although I will say there is a 200 millivolt setting, so it might do okay. So let me grab my snap circuit here. I'm going to have you try this if it works out nicely. Yeah, that works out nicely. Okay, let's build it. Let's build it. No need to like alligator clip and do crazy things with that. So let me grab the picture of this circuit for you. One of these pictures. Eventually, oop, I wrapped around. Hold on, I gotta refresh my window. Yeah, there we go. Okay, make it as big as I can. And let's build this one. I'll put it dead center. And that's going to be our little voltage divider. Okay, this black, I got lazy over here. I was building the circuit to look alike, and then this black lead, that's just me going, I don't want to find a 1, 2, 3, 4 and a 2, and I gave up at that point. So give that one a try. So build that one up real quick. I might have the battery backwards. I do have the battery backwards. That's okay. Build it like that. We'll deal with that. And then just let me know when you have that all snapped together. Casper's done. Josiah's done. Yeah, nothing. Hopefully nothing too crazy here. The battery's backwards. That one's on me. I should leave that up. I'm going to leave the picture up for now. Cool, Anna's done. That's 3. We got a couple more of you. Zoe's good. Cool. I'm counting on you, Shams. You got this. I know, I love the egg thing too. I think it's just meant to be like a cool glowy thing to put on top of the LED. So like if you want to build the LED circuit again, like stick the egg on top. Here. There we go. Am I still on the screen? Yeah, there we go. Right? Just like that. It is a sound kit. I think a maraca is an excellent idea. I love it. Gotta catch them all, man. I think I predate Pokemon, but my kids are starting to get into it, so just a little. Okay, so it sounds like everybody's got it built, which is awesome. And it sounds like you're exploring the kit, which is really all I want you to do. I can't do. There's hundreds of experiments between the two kits. We can't do them all, so I want to give you basic concepts and kind of. You're gonna have the kits for weeks ahead, so I really want you to play with it because that's learning should be playing on some level, and you got the tools in front of you, and now hopefully you know how to do some basic stuff with them. I love it. Yep. Okay. Yeah. Now, Anna's spot on. You got to test them all. So I flipped the battery around when I took the picture. I built it quick, and I wasn't paying attention. So here's how that changes our calculations. This is now -3. That's now -3. Oh, that's now -3, which is going to make the current be negative 576.9 microamps. And it's going to make all of these negative, if I can fit that in there. And that one's negative. Okay. That's on me. I flipped the battery the wrong way around. So you can do one of two things. You can look at all these negative signs, or you can just go flip your battery. But I think that 2 is going to cause some problems unless you kind of reshuffle how things are snapped in there. I think you're all sharp enough you can figure that out. Okay, so if it looks like this, I want you to take some measurements and just see that our voltage divider calculated things correctly. So let's play the stick your probes where to stick your probes. Okay, so take a measurement here. Okay, so I'm going to put a red probe there, and I'm going to put a black probe there. And I think we've already taken this measurement. That's VS. Okay, I'm going to stick a red probe here and a black probe here, and that's going to be VR1, and then a red probe here and a black probe here, and that's going to be VR2. Oops. You can, yeah, there's so I flipped the battery, so you can either call it negative or you can swap the schematic symbol, but that's going to make current flow the opposite way. I do apologize for that. But go ahead and take those three measurements, and hopefully they're going to match what we calculated with the voltage divider. Negative, Sham's coming in with negative 3.6. And I'm guessing that's over here. 3.16. 3.28 for Zoe. Cool. You got two 1.5 volt batteries in series, so they add up to be 3 volts. And yours are just have a good amount of charge on them, which is good. Two 2.46, 2.42, and 0.03. Okay, Casper's in the ballpark too. Sham's got negative. I'm going with Sham's numbers here. Negative 0.04. I'm guessing is that one. Did I miss one from Shams? I got 2 out of 3 from Shams. Okay. I'll grab Casper's since I can. I won't screw it up, and I also see that the numbers kind of line up nicely for me. Okay. Okay, so looking at Casper's numbers, we got 3.2 over here. 3.2 volts. And we've got 3.15 volts and 0.04 volts for those three. Okay, I think those kind of feel like they pass my gut check, and my gut check in this case is really doing KVL. If I add up these two and then I come down across here, these two should be the same added together as this one. So I got 3.15 and 0.04. That's going to be 3.19, and this one is 3.2. So they kind of pass my my gut check in that respect. And we got some negatives. Well, he didn't have negatives, but if you build it like me, backwards, then you'll have those negatives in front of there. Okay, so I think we're good in that respect, and let's look. We thought this one was going to be 0.06, right? Because this is really 40 millivolts. 0.04 volts is equal to negative 40 millivolts. Now, because that's on the small end of the measurement scale, I'm not surprised it's a little inaccurate. But then, let's see, this should have been 2.94, but that was with a 3 volt supply. So let's go through and do this in a slightly different way to check his numbers. And I'm going to write the equations the way that we typically write a voltage divider. Okay, so we were saying VR1 was equal to the current. Well, what was the current? The current was the voltage supply, and it was divided by, and I'm going to write that over here for a reason, the two resistances added together because they were in series. Okay, Then we took that current and we multiplied it by the resistance we were interested in. So we usually write the voltage divider that way. So let's use Casper's numbers, right? So we got 3.2 times, and just using the nominal values for VR1, this is going to be 5.1K, and there could be a little bit of part error, and that might be what's making our numbers have some error. Plus 100. Okay. And hopefully that matches what he got. Let's grab our calculator. 3.2 times 5.1K divided by 5.2K. Oops. 5.2K. Okay. And so I calculated 3.14. I hate that it disappears when I do that. 3.138. I'm going to round that a little bit. So I'm even adding some additional error by rounding. 3.14 volts. Okay. And what he measured was 3.15. So I'd call that in the ballpark. Okay. Now we can do the same thing for VR2. And it's going to look very similar because the current's the same, right? So it's going to be Vs over the two resistors in series. What's different is the numerator. Okay, so same voltage in. Now we've got the 100 ohm in the numerator. And let's figure out what that one should be with his numbers. Calculator, and I think I can even steal what I wrote earlier. It's not plagiarism if I'm stealing it from myself, right? Okay, and I calculated that I should get 61.5 millivolts, and we ended up with 40 millivolts. We're not that far off there. We're actually only 20 millivolts off there. Whereas here we were only 10 millivolts off, so there's a little bit of measurement error, and that's life. Okay, you have to have some comfort level with how much error is present in your measurements. Okay, so this was the first voltage divider, and it still has to follow KVL, right? These two voltages have to add up to this voltage. And that's kind of we can't create free energy. If we could, then we patent it and we all get out of here, right? We make a lot of money. But the way that these two add up is dependent on the resistances and the ratio between those resistances. So if I want to figure out how much voltage is across one of the resistances, I've got that resistance in the numerator and the sum of the two in the denominator. Okay, if I want to figure it out across the other one, I've got the other resistance in the numerator and the sum of the resistances in the denominator. So I've got this ratio of resistances. Because these are added together, and this is only one of them by itself, we can never create more voltage on any one resistor than we can from the battery. Okay, it's always going to be smaller in the numerator than in the denominator because resistances are always positive. Okay, this was the first voltage divider that I wanted to build, and we have this ratio thing going on. I want to build a circuit that we can play with the ratio a little bit more. I'm now the host of the meeting. Good for me. So let's build another circuit, and we're going to play with the voltage divider a little more. And I think I need a fresh sheet of paper because I can only fit so much stuff on these images. And let me go, well, let's talk about what it is first. So in the kit, Oh, I have a picture of this one so that I don't have to hold it up in front of the camera. Let me get the picture of the next thing we're going to play with. And it looks like that. Okay, so we're going to build another voltage divider, but we're going to do it with a single component. Okay, and it looks like that. And I take a, well, RV is not a bad designation for it. It's a resistor and it's variable. Where is mine? Okay, so I have, that's the big picture of the one I'm holding here. And it's got a slide, right? So I can grab that slide and I can move it up and down. So this is a way that we can change a value in the circuit. We can have a variable resistance. But there's a way that this thing is built, and it allows us to use it as a voltage divider, but it's a voltage divider that we can move to different values. Because we can do that, we can use it to either by varying the resistance or using it by a varying voltage divider. We can use it to change the volume on a stereo. If you're looking at older stereos, they might have potentiometers on them. They're cheaper than some of the new fancy digital knobs that you can feel the clicks on. Those are called digital potentiometers. This is an old-fashioned analog potentiometer, and we're going to build it into a voltage divider. Okay, so here, that's the component. The schematic symbol, you can kind of see it, and that's one of the neat things about snap circuits. You have the schematic symbol kind of hiding underneath it. Okay, so oops. It's got this thing pointing in, the arrow, and then the symbol, oops, is really a resistor. Okay, and we call it a variable resistance, or a potentiometer. Potentiometer, I think I spelled that right. And a lot of times, for short, we just say it's a pot. Okay. So it's got 3 terminals. And these 2 on the ends, we can call the end terminals. Terminals. And this one over here is called the wiper. Okay, so inside this thing is really just a chunk of material. I really want to split one open one day and get good pictures of it. Today's not the day. Someday I will. Okay, so it's got a chunk of material. I'm gonna do hand drive now to make this work. It's got a chunk of material, and if I measure the resistance from one side to the other side, it's going to have some resistance value. Okay, the wiper is just a little finger that slides back and forth on that material. Okay, so if the wiper is all the way over to one side and I measure the resistance from that side to the wiper, it's going to be 0. Okay, if I then measure the resistance from the wiper to the other side, I'm going to get the full resistance of the potentiometer. If I slide the wiper all the way to the other side and I measure the resistance from the wiper to this side, now it's going to be 0. Okay, if I measure it from the wiper to the original side, I'm going to get the full resistance. Okay, those are the 2 extremes, and I always like to look at the extremes of the situation. And then if I put the wiper in the middle, it's going to be some combination that adds up to the 2 terminal resistances. So I want to see that now. So take out the green thing. Where did the potentiometer? Oh, it's green. Look at that. It disappears into my green screen. So if I end up with a Death Star back there, you can see it through the chroma key takes it out. Okay, so grab the potentiometer, set your meters to stun. Now I've mixed up Star Trek and Star Wars, and that's never forgivable. Okay, so let me see what this potentiometer is across it. But we're going to set it down in the omega region. And you're going to set it up to be 200K. Wow. So you got to set it to 200K. So let me hold that up for you. If you can see it. So set it up so that it's in the 200K region of the resistance. Okay. Oh, that blew out my contrast. I don't think we're getting to capacitors today, Josiah. That's going to be the first thing we do tomorrow. Can I show you one more time? Ooh, magic. Where it should be. Yep. Oh, the meter? Yep. No problem. Let me make myself big again. So it should be 200K right here, right above this little blue thing, pointing down there. Okay, we're measuring resistance, and this, oh, it's backwards, I'm sorry. I put it backwards so when I point to things, they're in the right spot. Okay, yeah, it's backwards. Let me see if I can flip myself. Where's my transform? Oh. Transform. Flip horizontal. Hey, this is what I normally look like. Okay. Yeah, I'm sorry about that. So 200K in the omega range. Yeah, you are looking through a mirror. So hopefully I just unmirrored myself. We're playing a lot of games with that today. And this week. Okay. Whoop. There I am. Now I'm mirrored again. We'll figure that out. Thanks for sticking with me through that. Measure the resistance across the whole potentiometer. So from N terminal to N terminal. So measuring resistance. Oops. From there to there. And we want to make that an ohm meter, which is what you just set your dial for. So the schematic symbol is going to be a circle with an omega. And you just label it like this. So stick your ohm meter right there, 52.5. Okay. And because this is a lower end meter, since the range is 200K, then that 52.5 is 52.5 kilo ohms. Okay, so start with that. 52.5K. I forgot my... Oop. We'll just make that whole area black. That's just a little bit of cardboard. Okay, so I want you to do the same thing, but now I want you to measure without touching the wiper. Set it somewhere in the middle. Put the wiper somewhere, you know, maybe not even the middle. 48.6. Yeah, it feels like we're all around 50 kilo ohms. So I'm guessing it's a 50 kilo ohm potentiometer. And that 50 kilo ohms tells you that the resistance across the two N terminals are 50K. Okay, so set the wiper somewhere in the middle randomly. You can put it at a third, 2/3, half if you want to have things be close to each other, and then measure from there to there. Okay, if you can even see that white in the glare of the flash. Okay, and then do another measurement. Oops. Do another measurement from here down to here. Okay, so stick your ohm meter here and your ohm meter here and get those two measurements. Okay, 26.2 for Zoe. I'm going to use Zoe's numbers. Okay, so from here to here, she had, I'll do it in orange, 48.6 with an asterisk. And one or the other, I'm not sure which one, it doesn't really matter. 26.2 and 24.2. Okay, so again, we have a little bit of measurement error. Josiah's got 27.1 and 20.7. Let me see. And he had 46 across the whole thing. Yeah, so there's a little bit of error, but this is life. Okay, so what should happen is these two over on the left should add up to the one on the right. So let me be good and write my units out correctly so that I can try to get you to have good habits early on. Writing a unit with it is really important. Okay, and it's a habit that not many people have. 24.2 kilo ohms and 48.6 kilo ohms. So with any luck, what we have is two resistors in series that add up to the resistance between the end terminals. Wow, I can't say that word today. Wow. Okay, so 24.2K plus 26.2K. Well, what does that equal to? 50.4. I just did it in my head, but I don't trust my brain right now because I've been talking for a while. I don't trust my brain when I've been silent for a while either, to be fair. Okay, 50.4. 50.4 kilo ohms, and that should be approximately equal to 48.6 because that's all that's going on there. Alfredo's in here with 42.9. I like it. Shams has 49.8, so they all kind of feel like they're in the same ballpark. Okay. So the other way that we can draw the schematic for this potentiometer is to split it into two resistors. Okay, so we may see a potentiometer drawn this way, and they're going to vary, and because they vary, we put an arrow through them at a diagonal. Okay, I think there's another part in the kit too that has that. Haha. Yeah, there is a part. It looks like that. And it has the resistor with the arrow through it. It's just a variable resistance. So we can draw an equivalent schematic symbol out of two variable resistors, but they vary together. So we gang them together like that. So as I vary one, the other one varies with it. Okay, so as I make this one bigger, this one gets smaller. As I make this one smaller, this one gets bigger. Okay, so here's the circuit we're going to build. And I think this is our last circuit for the day. But we're going to take our battery. We're going to put it here. Okay. And we're going to connect it like that. So this is going to be about 3 volts. Some of you have a little higher. And then as the wiper's all the way up to one side, this voltage will be connected to the 3 volt directly. And as it's connected all the way down to the bottom, let's call this ground, it's going to be connected to 0 directly. Okay. So we can make this voltage divider, and we can take our 3 volts, and with a couple resistors in the form of a potentiometer, we can make that vary. So let me see if I have a good picture for you for this one. If not, I'm going to take a picture right quick. Oh, I did. I hooked it up to the LED as well. But we can do it with measurements. Let me rotate this. And get it as big as I can while still fitting on the screen. Okay, so that voltage, I took that voltage and I ran it through the LED so that you had a visual thing going on. This is where you can totally use the egg, by the way. Okay, this was the 100 ohm resistor. And I built that circuit, whoops, that looks like this. It looks like it's flipped from the way I drew it in the schematic. Let me get it away from my head. I think that's away from my head. Okay, so here's your voltage divider. The 3 volts is across the N terminals, and then we take the output of the voltage divider from the wiper. Okay, and then we just use that to drive the LED. So hook that one up, and then play with the wiper and tell me what you see. Yep, that's exactly what happens. Because as I bring that voltage up, there's going to be more voltage across the resistor, which is going to allow more current, and that's going to make the LED brighter. As you drop it down, there's going to be less voltage, and then ultimately there's not going to be enough voltage to meet that forward bias voltage of whatever the color LED has. Okay, so take a measurement for me then. I think other people are still building. Let's let other people build for a second, then I'm going to have you take some measurements for me. Oh, your light's not working. Uh-oh. Check your connections. Yeah, backwards would be the easiest thing to get wrong. Your battery could be backwards, or your LED could be backwards. Uh-oh. Oh, Zoe fixed it. Cool. Okay. Oh, good. It's working. So let's get some measurements. Okay, so let's see. Let's take a measurement. Red probe here, so just across the battery like we tend to do. But it's really the voltage across the whole potentiometer, right? Because the battery is in parallel with um, the batteries in parallel with the potentiometer. Okay. The next one are the two individual voltages. So take a measurement here. Without moving the slider, take a measurement there and down here. And let's call that VR1. And then take a measurement here. And the black probe here. And let's call that plus or minus VR2. Yeah, DCV 20 volts, or DCV on the 20 setting. .12. 2.14. Okay. It changes really fast. Oh, that could be because of the blinky LED. Boo, blinky LEDs. Cool. Especially if you put them in an egg. So, 3.12 volts, 2.14 volts, oops, and 0.96 volts. Those feel pretty close to me. Okay, because in that potentiometer, I'm going to take those values. Okay. Yeah, the egg is pretty cool. I hid that from my kids for now. In that potentiometer, so here's the 3.12. So here's some measured values. I'll put them in orange. 3.12 volts. Over here we had 2.14 volts. And the way I had you measure that, that's the polarity. And then down here is 0.96 volts. Okay, those are all going to add up, or be reasonably close to adding up. So 3.12 minus 2.14 minus 0.96 should be approximately 0. No, you don't need to use the egg, but it's just kind of a fun thing to put on there. It's not going to change the way the circuit works. But who doesn't love a good light show, right? Okay, so 3.12 minus 2.14 minus 0.96. Okay, 20 millivolts was my error there. Over 3 measurements, I think we're calling that pretty good. Okay, so if you move the slider to the other side and you do this again, you're going to get the same addition working. Okay, it's always going to add up. These two voltages are always going to add up to this voltage, but it's going to, how they get split, how they get divided, is going to depend on the position of the slider, and we can use that to vary how a circuit's operating. Okay, 323. I wanted to do capacitors today. We'll get back to that tomorrow. How are we feeling about potentiometers? And voltage dividers in general. 4? Cool. 4 is awesome. 3 to 4, 3, 5. Cool. Very good numbers. I love it. I love it. Okay. Let's see. What do I have on the schedule for it? 2-4. I'm gonna call that a 3, Jonathan. Somewhere between 2 and 4. Okay. All right. I think you can if you try. Let me find my little schedule here for what we're gonna do tomorrow, just so we can know what's coming. So let me go to camera so that I can rummage around my desktop a little bit. Come on. There we go. Let's see. So that's what I had originally. I think we're kind of on schedule. I'm a little glad that we had Tuesday, but I wanted to do energy storage and capacitors. So we'll start out with that tomorrow, and then we'll look at transistors and amplifiers. And we may get to play with some of the integrated circuits. I don't know that we'll get to digital circuits, but we'll try, right? So, does anybody have any questions for me? Everybody's going to go do something fun outside. Is it a nice day? I hope so. And we'll do more voltage dividers, transistors, and we'll turn those into amplifiers tomorrow. Okay? So I've recorded my feed directly today, so the quality is gonna be like way better when we upload a video, and we should be able to get it up pretty quick. So if you want to relive this magical time together, you can totally do that on YouTube. Yeah, I'll probably play some games too. But my kids are really into Minetest right now, or Minecraft, the free version of Minecraft, because I'm cheap. So they'll probably make me go build some things with them. Okay, thank you everybody. 326, I think that's pretty good. Yeah. They just started playing. It was like when we went into lockdown. Soccer's good. We went and played a little soccer last night, just with the kids, since their soccer season got canceled. We took them up to the field and played some games with them. They're young still, so they're not playing actual games. So, yeah, good walk. I'll take one after dinner too. So, awesome. Okay, thanks everybody. I'm still really impressed with everything. I hope you're learning a lot and you feel like you're taking something away from this. And I'll try to give you some more of that tomorrow. Okay? Yeah, yep. Okay. Take care. Have a good night.